To continue our discussion on section 6.3, we are going to go back to 6.1 and when we talked about verifying trig identities, and we are going to now include our double angle identities in the process of verification. Here I have the identity including a sine of 2 theta. So what I'm going to do first, since on the right hand side I don't have any 2 thetas in that expression, I am going to rewrite this sine of 2 theta by using one of my double angle identities. And that would be that sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. Now on the right hand side, I will also go ahead and multiply this right hand side out, because on the left I'm not sure how to manipulate this to get it to look like that right hand side. So what I'm going to do is just multiply out this right hand side using properties of binomials. So if you'd like, you can rewrite this as A, that would represent my sine of theta, plus B, which would represent my cosine of theta, all squared, which would then multiply out to give us a squared plus 2ab plus b squared. So when I do multiply out this binomial, I've got sine squared of theta plus 2 times sine of theta times the cosine of theta plus my cosine squared of theta. Now I do see that 2 sine theta cosine theta repeated on both sides. So that tells me that somehow I probably need to manipulate the remaining 2 terms on that right hand side so that they equal 1. And I do recall that sine squared theta plus cosine squared of theta does equal 1. So that tells me that I should rewrite, using the commutative property, my right hand side so that that sine squared theta and cosine squared theta are together, and then that does leave me with 2 sine theta cosine theta. So on the right hand side, this expression will reduce down to 1 by that Pythagorean identity, plus 2 sine of theta cosine of theta, and then on the left I've got 1 plus 2 sine theta cosine of theta. So I have simplified the left side, and I also manipulated the right hand side so that the 2 are equivalent, verifying my identity. Okay, go ahead and take a moment to pause the video and practice this next identity on your own. Now I know for tangent of 2 theta I have a couple of options. My first option is that it is equal to 2 times the tangent of theta over 1 minus tangent squared of theta. Or I have the option sine of 2 theta over cosine of 2 theta. Now on the right hand side I see no sines or cosines, no sines or cosines of 2 theta, so I think that bringing in the sine and cosine in this case is actually going to make things a little bit more complicated. So I am going to stick with all tangents and rewrite this left hand side as 2 tangent of theta over 1 minus tangent squared of theta. Now this is starting to look a little bit more like the right hand side, because on the bottom I do have subtraction, something minus tangent, and in the numerator I see a 2, so there are some similarities between the left and the right, but we haven't obviously gotten there yet because they are still quite different. One thing I know about the relationship between my tangent and my cotangent function is that cotangent is actually 1 over tangent. So if I multiply this 1 by 1 over tangent, I will get cotangent. And if I multiply tangent squared by 1 over tangent, I will get tangent. And that starts to look like the denominator that I have on the right. So I'm going to multiply this denominator by 1 over the tangent of theta, and then I will distribute it to that entire denominator. Now this is perfectly okay to do so long as I also multiply the numerator by 1 over tangent of theta. So doing this, I've got 2 when I multiply, when I distribute, tangent theta times 1 over tangent theta is tangent theta over tangent theta. And then in the denominator, 1 over tangent times 1 is 1 over tangent of theta, minus, and then 1 over tangent times tangent squared is tangent squared theta over tangent. And I want that to be 2 over the cotangent of theta minus tangent of theta. Well, I can do a lot of reducing here. Here my tangent's reduced down to just 1. Here I've got tangent squared in the numerator and tangent in the denominator. So in the numerator that reduces to just tangent of theta, and in the denominator that reduces to just 1. So on this left-hand side, my fraction will simplify to 2 in the numerator over 1 over tangent, which is cotangent of theta, minus tangent theta over 1, which is just tangent of theta. And that is equal to the right-hand side, which is 2 over the cotangent of theta minus the tangent of theta. Now, example, I was able to only manipulate that left-hand side so that it was equivalent to the right-hand side, therefore verifying my identity. However, we could have done some manipulation on the left and then on the right as well to show that those two things are equivalent. Moving on, we are going to talk about deriving reduction formulas. So double angle formulas can be used to derive what we call reduction formulas. These are used to reduce powers of a given expression involving even powers of sine or cosine. So that would be something like sine squared, sine to the fourth, sine to the sixth, etc. Even powers of sine or cosine. They allow us to rewrite those even powers in terms of just a first power. So what we are going to do is solve for sine squared and see what does sine squared equal in terms of cosine. So first I'm going to subtract my 1 from both sides. I'm trying to isolate my sine squared, so I start by isolating that whole term. So I've got cosine of 2 theta minus 1 is equal to negative 2 times sine squared of theta. Now I divide everything by a negative 2 to isolate my sine function. You can write it as one big fraction. I chose to write it as two smaller fractions. So here I've got negative cosine of 2 theta over 2 plus 1/2 is equal to sine squared theta. So what this has done is it has taken my sine squared function and written it in terms of a function that is not squared. So here cosine is just to the first power. So we can use this to simplify those exponents down into less complicated versions of our trig functions. So here are our reduction formulas. We could go through the process for all of these using the identities that we've been given. However, we're not going to do that today. It will be valuable to make note of these reductions formulas though, so that you can utilize them in your work later. That concludes our video for today and section 6.3. Thanks for watching.